Okay, well, good evening, ladies and gentlemen. It's my pleasure to welcome you to tonight's presentation in the 2008 von Karman Lecture Series, and thank you all for joining us. Before I introduce our speaker, let me invite you to next week's von Karman lecture, The Importance of Sample Return, about the Genesis mission. You can read about it in the flyers that are out on the counter. It returned samples from the solar wind to Earth in dramatic fashion. That'll be on April 24th here and April 25th down at Pasadena City College. Places in our solar system that are known to have liquid water are rare. But the evidence Cassini has collected during flybys suggests that Saturn's little moon Enceladus could be one of those places. I recently heard a TV newscaster pronounce it enchiladas. Our speaker tonight will show you huge icy geysers continuously erupting from the south polar region of Enceladus. Imaging and compositional data from Cassini's close flybys may provide clues to understanding how these geysers originate. Tonight's speaker, Amanda Hendricks, is a research scientist at JPL. She's a member of the Asteroids, Comets, and Satellites group. She received her BS in Aeronautical Engineering from Cal Poly in San Luis Obispo, and her master's from University of Colorado at Boulder. Her PhD work there included analysis of ultraviolet spectroscopic data of the Earth's moon and Jupiter's moon Europa, and she continued her research with UV spectroscopy as a focus, studying the moons of Jupiter, including sulfur dioxide on Io, radiogenic products on the surfaces of Europa, Ganymede, and Callisto, and studying water ice on Saturn's moons. Amanda also uses ultraviolet spectroscopy to study space weathering effects on asteroids and the moon. She was a co-investigator on the Galileo ultraviolet spectrometer team and is a Cassini ultraviolet imaging spectrograph team member. She's also a member of the Cassini science planning team. Amanda also runs research programs as a principal investigator for NASA, and she likes to water ski and will be planning to skydive for the first time on her birthday. In 2006, Amanda received the JPL Lou Allen Award for Excellence. Please help me give a warm welcome to our excellent guest, Dr. Amanda Hendricks.
Thanks, Dave, and thanks to everyone for coming tonight. Let me bring up my presentation here. So I'd like to tell you the story of Enceladus tonight and start by going back from what we first learned about Enceladus from early on in history and then take you through time to what we know about Enceladus from the most recent flyby from the Cassini spacecraft, which just happened last week. Why do we want to study Enceladus? It's a very interesting body, but one of the reasons that it's so interesting is because it's so little and icy, and it's just so unexpected that so much activity would be happening here. It was discovered in, 1789, I think, by Herschel, and that was about 100 years later than some of the other icy moons of Saturn were discovered, like Rhea and Dione. And this is because it's small, for one thing, but it also orbits in pretty close to Saturn. It's only about 4 Saturn radii out from the planet. So when you're looking from Earth at a small body that's close in to a bright planet and the bright rings, it's hard to actually distinguish it from the body. So it wasn't discovered until a little later when telescope technology got to be a little bit more sophisticated. I was talking about how it's a small body. Here's Enceladus compared with some of the other moons in the solar system. Here's Enceladus. It's only about 500 kilometers across. And here's the Earth's moon to scale. And so Enceladus is only about 15% of the size, diameter-wise, of the Earth's moon. So it's very small. Here, just for comparison, Rhea, Tethys, Mimas, Iapetus, and Dione are some of the other icy moons of Saturn that we study with Cassini. And here, of course, is Titan, which is characterized by its very thick atmosphere, so we can't actually see through to the surface with our eyes. Titan is bigger than the Earth's moon, but it's actually the second biggest moon in the solar system. So we're studying Enceladus because it has intriguing characteristics, and we've known this for a while. One of the first things that's intriguing about it is its high albedo. Oh, here we go. And that means that it reflects a lot of the light that hits its surface, actually almost 100%. It's very bright. And this has been known since early on, after its discovery. For comparison, the Earth's moon reflects about 8% of the light that hits it. And we're talking about, we look at the moon and it looks pretty bright to our eye, but actually, since it's made out of rocky material and not water ice, it's pretty dark. So Enceladus is made of water ice. It's not completely made of water ice. We know that it's denser than water ice would be, so we know that there's rocky material interior, but the surface is primarily water ice, so that helps it be very bright. We also know that Enceladus orbits at the densest part of the E-ring, and this is interesting. I'll tell you why. So the E-ring, we all know the main rings of Saturn. They're beautiful and fabulous. Here they are up close. This is the A ring, the outermost of the main rings. The Encke gap is within the A ring. Then you have the B ring going in, and the Cassini division divides the A ring and the B ring. And then the C ring. And inside, here's the planet in here, inside is actually the D ring. So they were named going in, and then more rings got discovered. For instance, this is the very thin F ring. The E ring, I'll show you in this artist's conception, is out here, and it's more diffuse and broad, and you have to really stare for a long time before you can see it. But it's out here, and this is where Enceladus orbits, right in the middle of the densest part of it. But the E ring actually covers, E ring material actually extends from Mimas all the way out to past Rhea. So let me go through this a little. Here's the planet in the main rings. Here's Mimas, Enceladus, Tethys, Dione, and Rhea. And the E ring is densest at the orbit of Enceladus. So that is something curious. We've always thought, is there some relationship between Enceladus and the E ring? Also, we've known since the Voyager days that there are very few craters on Enceladus compared to other moons that we've studied. This is a Voyager image from the early 80s, and we can see that there are broad swaths of terrain where there's barely any craters at all. It's very unique. There are regions that are pretty cratered, but then there's entire regions that don't have any craters at all. And that's very unique. You know, you think about our own moon or other moons that you've seen images of in the solar system, and they're pretty heavily cratered. So all of these characteristics suggest that it's a young surface. That means that it is probably being resurfaced by some sort of geologic process. And maybe there is some current or recent geologic activity happening, which is pretty interesting because there aren't that many bodies in the solar system that exhibit such activity. So as early on as 1981, this artist's conception appeared in National Geographic, suggesting that there were some sort of cryovolcanism or geysers appearing on Enceladus, because we knew even since the Voyager days that something funny was going on there. So what other bodies do we have in the solar system that are geologically active? The Earth. Here's a geyser on Earth called Old Faithful. What else? We have Io. Io is this moon of Jupiter that's actually the most volcanically active body in the solar system. This is a gorgeous color Galileo image of Io. almost everything that you see on the surface, all the different colors and all the different features are related to volcanic activity. And then, of course, we have this plume here on the limb that you can see. This is a nice sort of animated image from the New Horizons spacecraft that just flew by the Jupiter system about a year ago. And you can see this very dramatic Tvashdar plume up in the northern hemisphere there. And then there's another plume down here, too. Triton is another body that exhibits cryovolcanism. This is the moon of Neptune, and it has polar caps, actually, this strange cantaloupe terrain, and a tenuous atmosphere that is probably fed by cryovolcanic processes. And finally, we have Europa. Now, we can't say for sure that Europa is currently active, but it sure has some terrains that look like they've been at least recently moved around by some sort of process here. This is what we call the chaotic terrain, or the chaos region, and it really looks like there's blocks of material that have been tilted up by subsurface motion, maybe of a subsurface ocean here. There's cracks all over the surface, and all of these surface features and different colorations make us think that something could be happening on Europa today, causing subsurface ocean material to upwell through the surface and get extruded onto the surface. We don't know for sure, though. So this is a pretty exclusive club. I'll also mention, of course, that Mars and Venus have extinct volcanoes. But this is a very exclusive club for Enceladus to think about joining. So it's exciting. Okay, so now we're into the Cassini era. We know that Enceladus is a very interesting target. And now we have this spacecraft launched in 1997 on its way to Saturn. Here's the Cassini model right over here. It's the half size, so it's actually twice as big. And it was launched in 97 and it arrived in 2004. So we've been there for almost 4 years. And one of the main goals of the mission was to study Enceladus. So what we did was we planned out a tour of the Saturnian system with 3 targeted flybys. Here's another graphic showing a couple of sides of the Cassini spacecraft. The instruments that are on the orbiter include cameras. There's 4 cameras, the visible cameras that we normally see images of, a near-infrared instrument, which is called VIMS, and a far-infrared instrument, which is called SEERS, and you'll hear me talking about these instruments. And so, of course, the infrared is longer wavelengths than the visible. And in particular, the SEERS instrument is used to measure temperatures. Very important at Enceladus. The UVIS is the ultraviolet instrument on Cassini, and that, of course, measures ultraviolet wavelengths, which are shortward of what our eye can see. Then we have the MAPS instruments, or magnetospheric and particle science instruments. There's 6 of them, and they measure basically ions, neutrals, and different charged particles that make up the magnetosphere and also the environment around Enceladus. In particular, you'll hear me talking about the INMS, which is the ion and neutral mass spectrometer. The magnetometer is another thing that's made key measurements at Enceladus. And then also on board we have radar and RSS, or radio science subsystem. So I told you we have 3 targeted flybys planned for the prime mission, which is July 2004 to June 2008. The first targeted flyby was March 9th, 2005. And that was at a distance of 500 kilometers. And we got interesting looks at Enceladus. Again, we can see a sparsely cratered object, but that there's, I don't know if you can see very well from out there, or if it's kind of washed out, but there are color variations. Now, this is a false color image, but it's been enhanced to show color variations. There are cracks and different sort of regions that seem to show, that appear bluish when it's in a false color mode, and that seems to indicate larger grain materials, probably. One of the other, besides imaging, on that March 9th flyby, we did a stellar occultation with the ultraviolet instrument. And what that means is that we stared at a star as it passed behind Enceladus. And we watched the signal, and if there's any sort of atmosphere around the body, then the starlight is going to diminish as it's absorbed by that, the atmospheric gases. And so this is a very sensitive technique for measuring gases around bodies. So we did this measurement, and the stellar signal did not decrease as we approached the body at all. It dropped right off like a rock just as soon as we hit the limb of the body. And so that tells us there's no gases around the body at this location here. So no atmosphere at Enceladus. Strangely, though, and this is sort of interesting and frustrating, the magnetometer measured that the magnetic field of Saturn was perturbed around Enceladus, suggesting that there's some sort of material, some sort of gases, neutral gases around Enceladus that are sort of causing the magnetic field lines to drape around the body. So this was really interesting because the ultraviolet instrument didn't measure any gases around the body, and yet the magnetometer measured the inference of gases around the body. So this was a mystery for a little while. But the other thing is that this was such an intriguing result, and there was also a flyby that I didn't mention. It wasn't a targeted flyby, but it was a pretty close flyby in February of 2005, a month before this one. And the MAG team, the magnetometer team, used the data from that flyby and this flyby to get this result. And they were really interested in this. And they convinced the project that the next flyby that was going to happen in July of 2005 needs to be closer. It was planned to be, I think it was supposed to be 1,000 kilometers from the surface. And the magnetometer team said, we've got to investigate this more, and we can't do it from 1,000 kilometers. We have to be closer to 200 kilometers from the surface. So we had between April, when the MAG team came up with this result, and July to say, wow, we got to change the trajectory of the spacecraft. And that is non-trivial. But we did it. And boy, are we glad that we did it. Because on the second targeted flyby, July 11 of 2005, we really hit the jackpot. The trajectory was lowered to 172 kilometers. So the spacecraft team that worked so hard to change the trajectory and everything that went along with it really needs to be congratulated and thanked for doing that so successfully. What happened was we flew by on a very inclined trajectory, and we came up underneath the South Pole and got a very good look at the South Pole. And this is what we're looking at right here. The South Pole is basically centered on this cracked terrain that we refer to as the tiger stripes. We got a kind of a glimpse of these from the previous flyby. You can kind of see like just this area here. But now we see them straight on. And this is a unique feature. You don't see this every day in the solar system. So we know something funny is going on there, right at the South Pole. Even more intriguing, though, was the Sears results. So again, we flew up right underneath the South Pole, and Sears was able to measure the temperatures of the surface there. What they expected was something like this on the left here, where they'd have increased temperatures measured near the subsolar point. And then, of course, the poles are cold, so it would be cold down at the pole. And by the way, they predicted that the maximum temperature would be about 80 Kelvin, so that's about minus 300 Fahrenheit. So still pretty cold, but and then at the poles it would be probably minus 350 Fahrenheit or something. Instead, what they measured was this. Not only was the hottest region not at the subsolar point, it was at the South Pole, and it was a lot hotter than they thought it was going to be. So that was really interesting. And you can get a closer-up view, found that the hottest spots seem to correlate, and this is still pretty low resolution, but you could kind of see that the hottest spots correlated with these stripes. And these are temperatures here in Kelvin for each of these Sears pixels. So that was certainly interesting. And this is, again, a sort of a coarse resolution Sears map of the South Pole. So we're looking straight onto the South Pole here, and you can kind of see the image, the visible image in gray underneath, and here's these tiger stripes. There's basically 4 that we talk about along here. And the different colors refer to different Sears temperatures. And again, the resolution is sort of coarse, but the hottest temperatures that they measure in the orange and red lie on top of these tiger stripes. So let's see, I should have pointed this out, but the red arrows here, kind of guide your eye where the tiger stripes are. And the hot spots that Sears measures, the hottest regions, are labeled here. Here's D, C, B, G, E, F, and we'll come back to those. So this is really an interesting result. Also, remember the purple magnetometer graphic that I showed you from the first flyby. Now, the mag guys, the instrument got so close that they could actually say the neutral gas that they used to think was probably global because of the lower resolution from the more distant flyby. Now they can tell it must be concentrated at the South Pole. So even just from mag results, this is the kind of picture that they came up with. And this is super lucky and serendipitous, but we did another UV stellar occultation on this flyby, and we watched the star pass right behind the South Pole. And not knowing that anything was going to be happening at the South Pole, that's just where the occultation happened. And sure enough, the star measurement, the stellar signal, drops off as we get in close, and then completely drops off when we hit the limb. But this attenuation of signal tells us that we have encountered some gas, some vapor. And since we didn't up here on the previous flyby, that tells us, well, it must be a localized atmosphere. So everything is really kind of hanging together. Now, what is the composition of that gas? The UV instrument could tell that it was water vapor. It was primarily water vapor, and that result was backed up by the INMS that I mentioned, the ion and neutral mass spectrometer, who can measure other species too, a lot more species than the UVIS instrument. And they said, yes, it's primarily water. There's also some CO2, some nitrogen, methane, probably some CO, and trace amounts of other species like hydrocarbons. So this is really exciting. Let's see. Now, so this is, first of all, let's just step back and think about how crazy this is, that there's this gas coming out of the South Pole and out of a big hot spot on the South Pole. But it doesn't look like anything to the eye. The images didn't show us anything. And that's because the geometry wasn't quite right. But later that year in November, we had the opportunity to be pretty close to Enceladus. It wasn't a targeted flyby, but we were pretty close. And it was also high phase. So we're just seeing the crescent of the moon. And that's the perfect opportunity to see dust particles, like when you see smoke, for instance. And now we can measure the plumes. They're backlit. And these very small particles forward scatter, and so they're being backlit, and this is the best opportunity to see them. And even more interesting is now we can see that it's not just a big plume, but it's a big plume made up of small jets that seem to be coming from very specific sources and pointed in slightly different directions. So, and in this geometry, also I should mention that we're looking sort of broadside to those tiger stripes. Now, and this is basically a stretched out version of that image here. So you can see the gas, or the plume, the ice jets are down in here, and then if you really stretch it out, you can see the very fine contributions really extend all the way out to here. And I'll remind you also that the camera, those high phase images that I just showed you, that's showing us ice particles. So the plume is made up of different gases that can be seen by the UVIS and by the INMS. And the composition and the density can be measured by those instruments. But the camera can actually measure the particles. And so we know that the plume is made up of different gases and then also ice grains. Now, it turns out that the camera had actually measured or observed the plume, before the other instruments had, back in January of 2005. But it was so unconvincing. We just all kind of looked at these images and thought, is that an image artifact or something wrong with the camera? It just seemed really unbelievable to think, hey, look at that. But now, after November of 2005, they could go back into the database and say, yeah, now we believe it. Now we think that's the plume. And then you can stretch it out and really pull out the contrast there. Another example of an early plume image is here, back in February of 2005. So, and now there's even more plume images. We look at Enceladus every opportunity we can at high phase. We want to see if it's changing. We want to see it at different angles to try to see where the jets are and how much ice they're putting out. And so what some of the researchers on the camera team have done is actually put together all those images and triangulated to find the exact sources of those jets. And so here we are looking directly at the South Pole again, and here's our 4 tiger stripes. And by the way, the International Astronomical Union, I think the IAU, which is in charge of naming everything in the solar system, has said that all of the features on Enceladus are to be named after characters and places in the Arabian Nights. So the tiger stripes are called Damascus, Baghdad, Cairo, and Alexandria. And we'll hear about some other similarly named features too. But anyway, so you can triangulate and find the sources of the jets. And they're marked here by these Roman numerals in yellow here. There's like 8 or 9 of them. And what's also shown here in red is the sources where Sears measured the hot spots in that one flyby. Remember we talked about A through F. And so we do find that many of the jet locations measured by the camera correlate with many of the hot spots. It's not a complete one-to-one correlation, but it's pretty good. Okay. So I'm waiting for this to advance. Okay, here we go. So another thing that we've done more recently is another stellar occultation with the UV instrument. And remember how I told you, okay, we had that one occultation that kind of went up here at kind of low latitude and measured no gas. And then the real jackpot was when we watched the star go right behind the South Pole. And that was kind of a vertical crossing, though. It kind of went like that. Now what we just did in October of 2007 was we had the opportunity to watch this star pass in a horizontal path right below the South Pole limb of Enceladus. So this is so perfect for looking at that plume and looking at the jets. And this will be the first time then that we can actually see gas jets, because remember, with the ISS, we're looking at particle jets. So here's the star passing right below the limb of Enceladus. And it's also perfect because it's not passing actually behind the disk. It's just it's only being occulted by the plume. And what we find is that, I hope you can see this graphic on the left. It shows you, this is versus time. So it's basically the density of the plume as the star goes through. And so as the star kind of hits the plume, it gets denser, denser, denser. Oops, there's some wiggles in there. I wonder what those are. And then it goes out of the plume. And so what we find is that these wiggles in here can be pretty well characterized by jet locations. And so on top of a broader gas plume, this broader shape here, we also see jets of gas coming out. And we can kind of correlate those with the particle jets that have been detected by the camera. If you the viewpoint of the UVIS was kind of along this direction here. So we kind of can't tell in this direction where they are, but we know that they must line up somewhere along here. And this first jet here lines up with these. Remember, look in yellow here for the particle jets. Lines up with these particle jets. The second gas jet lines up with this particle jet, and so forth. So there's about 4 of them. So this is really interesting. So now we're starting to put together a lot of the vapor and a lot of the particle stuff. And I'll also go back and remind you that one of the interesting things about Enceladus was that it orbits at the densest part of the E-ring. And we also can see now it actually contributing to the E-ring. This is a very high phase image. So the sun was, this is basically Enceladus in shadow here. And again, I don't know how well you can see this, but Enceladus is dark. It's a very tiny dot here. And so much of what you can see here is backlit, very fine grains, both in the plume right below Enceladus and in the broader E-ring. And you can see sort of tendrils of material coming off Enceladus and being deposited basically in the E-ring. So it's pretty fabulous. So what is the deal here? This is a crazy situation here. We have lots of heat and crustal deformation that is seen at the South Pole. What is the power source there? We have jets of gas and ice coming from these south polar cracks. What is the jet source? These are all questions that we have to try to answer with the data sets that we have. And also, why is it only at the South Pole? What a bizarre place to have cryovolcanism. So let's think about what people have been doing with the data sets. The heat source. Tidal heating is a pretty good resource for heating. Tidal heating comes when an object is in orbit around another one and it's in an eccentric orbit, so it's not quite circular. And so as a result, the body will get stretched out. And this happens with the Earth's moon. The Earth, well, that's why the Earth has tides, and the moon actually has a tidal bulge to it too, because of the pull of the Earth's gravity on it. And so what happens is that the body that's in orbit, in an eccentric orbit, gets flexed, and it creates heat on the inside from the friction. Kind of like if you squeeze a tennis ball or some other squishy ball, it gets kind of warm. So you've got frictional heat in there. Now, Enceladus is in an orbital resonance with Dione, that moon that 2 moons out. It's in a 2-to-1 resonance. So that's what keeps it in this eccentric orbit. Now, it's probably the amount of tidal heat, though, that's generated is probably not enough to explain the amount of heat that we're seeing now. What probably happened is that there was some sort of heat generated early on in the history, and then the tidal heating is enough to just keep it going. Probably the leading theory on that is that there was aluminum-26 present, which decays and produces heat. And so that produced enough heat initially to sort of kickstart that, and then the tidal heating can keep the heat up. So it's probably enough heat on the inside then to create this heat that we measure then coming out at the surface. What about the plumes themselves? Where can that vapor and gas, where can the vapor and the gas particles be coming from? Well, there's a few models out there now. One of the leading ones is from the imaging team, and they suggest that there's near surface liquid water. Okay, so there's some sort of an ice shell, and then below it there's liquid water, and it's so hot that it's boiling, and it must be fairly near the surface, and then you've got these cracks that we can see, and the water underneath is at high pressure, and the pressure is released basically through the cracks. You might have an ocean farther down, or some sort of a liquid source further down, but then frictional heating of the cracks will warm up the vapor and allow the plumes to be emitted as plumes of vapor and particles. This model here might not explain properly, though, the surface features that we see, the amount of activity along each of the tiger stripes. One other idea is that, okay, maybe there isn't a subsurface ocean, but there are clathrates, which are molecules basically that act like a cage. And they can basically trap different gases And so in the lattice, so if the clathrate is decomposing, it can release the gas, and that would be the source of the water vapor. It doesn't quite do it, though, for the amount of water vapor that we see. And then finally, you might have, again, a water reservoir and the vapor condensing into the ice particles as it goes up the cracks. So none of these, we can't really say none of these or any one of these doesn't work yet. But notice that 3 of them require a subsurface ocean or a subsurface water source. So that's kind of the going theory right now. And this is sort of a graphic showing what that might look like. This is for the first model where it's at actually boiling. So you've got this pocket. It's pressurized. It's down deep enough that it's pressurized. And then, just so long as it has a vent to the surface, which are those cracks, it's going to come up both in the form of vapor and particles. Notice down here that you have tidal heating to help heat this and keep this liquid under here. Now, why does it end up being at the South Pole? Well, this is actually where it's dynamically going to end up. If you have a pocket or an intrusion or what's called a diapir of low-density material, like a water pocket, if it originally maybe started at a lower latitude, it's actually going to reorient Enceladus because it wants to it's most dynamically stable along the spin axis. So this is where we actually would expect it. But the tectonic patterns that we see on the surface, the different cracks and stress fractures that we see, are actually consistent with such a reorientation having happened. If there is this low-density anomaly down here, which we would expect if there's a subsurface ocean or a pocket of liquid water, it might be detectable by Cassini. And so what we might want to do at some future time is do a close flyby underneath the South Pole and compare the mass determination with one from a low-latitude flyby. So let me tell you that the second flyby that we did, the July 2005, where we discovered all of the activity, it was called the E2 flyby. It had a trajectory that looked about like this. And this plot here, and I'm going to show you a few of these, so I'll explain it. It's symmetric about this axis right here. So this is Enceladus, and here's the plume coming out of the South Pole. And the trajectory for E2, remember I said we came in over the South Pole. Since this is, we kind of came in, swooped over the South Pole, and actually kind of kept going up. So by the way, here's the plume. This is basically the dust plume here, stretched out. So you can see that we kind of barely just went through there. We kind of nipped it. And already we could get good measurements on the composition and the density. Now, we just had another flyby last week, and we decided to get bold, and we went like that. We didn't actually bounce. It just kind of went going just like that. So here's what we flew in from the north all the way through. Our closest approach was at close to the equator at about 50 kilometers. So remember, our closest approach before was at 172. So we're really feeling brave, and we went 50 kilometers. The important thing is that it got us a lot deeper into the plume. Now, still, we were being a teeny bit conservative because initially we were going to go 25 kilometers away. And that would have put us even deeper into the plume. But then we decided, well, let's back off just a little bit and make sure we understand the plume a little bit more before we go that deep in. But still, this was really exciting. And 50 kilometers from the surface, that's closer than we've gotten to anything in the Saturn system. So it's really exciting. Now, this is a flyby. This was the third Enceladus flyby. I told you there were 3 in the prime mission. It just happened last week, so it's known as E3. And in this flyby, we're focusing on sampling the plume and on south polar temperature measurements. So we come in, we do some observations of the North Pole, and I'll talk more about this. And then what we do is we're doing a big turn. We're not pointing the cameras at the surface the whole time. It's a very fast flyby, by the way. If we were trying to take images of the surface through the whole time, they'd just be smeared, and we wouldn't be able to track the body the whole time and everything. So what we do is we're doing a turn, and we orient the spacecraft so that the INMS, the neutral and mass spectrometer, can basically taste and smell and touch the plume material and measure it and say, what's it made out of when it's going in here like this. So this is really exciting. I'm going to tell you about some of the results, but not all of them, if my computer will wake up. Okay, so I'm going to show you a movie to show you the geometry. Okay, hang on just a sec. Sorry about this. I can't find it on here. Okay, I'm going to show you this movie. Okay. I'm actually having a little problem here because I can't see the whole thing, so I can't stop it and start it. But look at this. Here, this is showing you what Cassini is doing. And so we start out very far away from Enceladus, and we're getting in closer and closer. But this shows you, okay, we're looking with the cameras, we're taking pictures. Now we turn, and we're doing a radar scan. The radar is oriented 90 degrees from the cameras. Then we turn back. We're still inbound, and we're taking more pictures. And we're doing scans with the UVIS, and the SEERS is doing temperature maps of the North Pole. We're getting in closer and closer. And now we're doing the big turn. And we're orienting the spacecraft so we can do the in situ particle measurements. Whoop, there goes closest approach. And then we do a turn and point again at the South Pole. And now SEERS is taking over and doing temperature maps. We do a little radar again, and then we do SEERS again. And we're going to end with a UVIS compositional map. Now, what this movie didn't show you is that right at closest approach, or right very close to closest approach, Enceladus actually went into eclipse. So it went into the shadow of Saturn, basically. And this was actually ideal, because when SEERS is looking at the South Pole right after closest approach, nobody else actually wants to look. The cameras don't want to look because you can't see it. But it's perfect for SEERS because there's no influence of the sun to heat up the surface at all. All they're looking at is the temperature that's coming out of the inside of Enceladus. So it's perfect, actually. Okay. There was the movie. So I told you that the inbound, we took images of the North Pole, and this is what it ended up looking like. This is, you can see that the phase angle is maybe 100 degrees or 90 degrees or something. But this is cratered terrain. We had seen it with Voyager a little, but not at this good of resolution. And over here, actually, this terrain here, we hadn't really seen with Voyager very well at all. So this is the best resolution North Polar imaging that we have right now. It's interesting to compare it to the South Pole, which, as we know, has very few craters. Actually, no craters on the South Pole. So this is cratered, but it's not completely cratered. Look at this swath over here and this swath over here that exhibit very few craters, and they look like they've been tectonically disrupted. These craters in here, this one is called Aladdin, I think, and this one's called Alibaba. They, I'm not kidding, they look funny. They look like they hit a surface that maybe was a little slushy or something. Like there's evidence there for some sort of heating of the surface at some point in the past. And it looks like it's been tectonically disrupted, but certainly nothing like what we see on the South Pole. So this will be a source of further study, further comparisons with the South Pole. Now, SEERS is one of the stars of the show of this flyby. And this is, again, in the gray image in the back, is our image of the South Pole that we've looked at a few times. And we can see the tiger stripes here, along here. And superimposed on that is this temperature map that Sears measured from the July 2005 second targeted flyby, with the contours showing the temperature ranges. And this is kind of a different one than I showed you before, but basically what I want to show you here is that the best resolution that Sears had in the previous flyby was about 25 kilometers. So their pixel was about this big here. In this flyby that we just did last week, they're going to get such good resolution, or they got such good resolution. Their pixels were like this big. It was like 10-kilometer resolution. So they're going to be able to resolve the tiger stripes. They're going to be able to measure the temperatures along the tiger stripes. And it's really going to be great. Okay, I wish I could tell you. Okay, the other thing about this E3 flyby is that since we're going through the plume, the INMS that told us about the composition of the plume so nicely last time is going to be way deeper in the plume. And so its resolution is much better. It's going to be able to tell us in much greater detail what the components of the plume are. So that's really going to be exciting. Now, we have more coming. We have another flyby planned that's coming up in August, and we're going to be even a little bit more daring next time. That's going to be called the E4 flyby. And we're going to be 50 kilometers from the surface there too, but we're going to get a little bit more deeply into the plume. And on that flyby, we are going to focus on imaging. So, and this is important, let me tell you too, because we need to get good images of the South Pole because before too long, the season's going to change on Enceladus. And the South Pole is getting more and more into darkness. It's going to be winter in the south. And so we've got to do imaging while we can. So on this flyby here, we're going to orient the spacecraft so that and again, this will be a fast flyby, but just as soon as we can, we're going to start taking images of the South Pole and get the best resolution ever of those tiger stripes. And we'll get temperature information too. So that'll be a really exciting flyby. This, and again, I don't know how well you can see this here, but here's our famous, tiger stripes. This line right here, and you can see that it's sort of stippled over here, shows you where the terminator is. So this will be nighttime during that August flyby. And these little white boxes here, it starts little and then it kind of gets bigger, bigger, bigger. This is the image. This tells you about the imaging resolution. So this is the size of the narrow angle frame. We'll get super good resolution down in here where we don't really have that good of resolution so far. And then as we pull away, the resolution will get worse and worse, but still great. So this isn't for sure. We'll use the information from this past flyby, this last week, to decide exactly on the placement of these fields of view, but it'll be something like this. It'll be really great. So I encourage you to stay tuned, because not only do we have the August E4 flyby, we have October E5, another one in October called E6, and then more later in the mission, E7, E8, E9, E10. And we are getting bolder and bolder with every flyby, because here's the ones that we already talked about. Later on, we're just going to go right on in and just cut through the densest part. One thing I didn't mention too much was that we kind of backed off a little on this last one and decided to be a little conservative, but we do care about the safety of the spacecraft, and we do really spend a lot of time making sure that the spacecraft is going to be safe flying through here, because there are dust particles, and we don't know. We don't want to have one that's big enough to really knock us out hit us. And so we spent a long time making sure that that wouldn't happen. And sure enough, any particle that's big enough to damage the spacecraft, we have pretty good confidence isn't going to make it up, this high where we are. They're probably, if they even exist, if such particles exist, they are not making it very high up. So we have pretty good confidence that we're keeping the spacecraft safe. And we do want to go in the future and make really good measurements close into the surface. So please stay tuned, and thank you for coming tonight, and thanks for all of your support.
All right. Thanks, Amanda. And we do have some time for some questions. I'll let you pick the...
Oh, okay. Any questions? Hi.
So you would expect maybe even despite the low gravity, some deposits if there are some larger particles. Is the blueness, you mentioned larger particles or larger material near the tiger stripes. Is that any evidence of broken or deposit material at the volcanic fissures?
Right. So just to repeat the question in case people didn't hear it, you know, we looked at the blue stripes. In that false color image, the tiger stripes look blue, probably because of larger grains. And why is that? Is that redeposited material or what? And we don't know, actually. It might be redeposited. It might also just be grains that have sintered together, so they become larger because of the heat. They sort of, you know, grow and glom onto each other. It's not clear. So far, we're really not seeing any direct evidence of, although we're looking, and there's some suggestion, but we're not really seeing any direct evidence of fallout from the plume composition-wise, but we are definitely looking. What we do see probably is very, like snow covering the surface, very fine-grained snow all over the surface. That's probably E-ring grains that basically coat the surface because it orbits in the E-ring, so all the E-ring grains hit it. And so, yeah. Yeah, Leo.
So you mentioned that there are some results that you couldn't mention. And we know about those results.
Right. So we have really, really spectacular results from the flyby last week. And I am dying to tell you about them, but I can't because they're so great that there's going to be a big NASA press conference next Wednesday. And that's when the world will find out about them. So watch your TV on Wednesday night for the really great results and read the paper on Thursday.
Those tiger stripes look familiar when you consider the surface of Europa.
Right.
And I was just curious whether any of the geologic action that we're surmising is happening on Saturn's moon. Have we seen any evidence in Europa of the same sort of action as something that's similar?
Right. Good question. Europa, we do see cracks on Europa, like the tiger stripes. Not exactly like the tiger stripes, because the tiger stripes are unique and we don't actually know why. They're so uniformly spaced and parallel. That we don't really see on Europa. Europa is kind of more random, although there have been features correlated to the diurnal stresses, the diurnal tidal stresses on Europa, but they're more curvilinear. Europa also, and we don't see this on Enceladus, but Europa's cracks, a lot of them are darker along the middle, and they're called triple bands because they go sort of bright, dark, bright. And that seems to be material that has come up from underneath. And it's actually different compositionally. And so far, we don't see that on Enceladus. Europa is, you know, very heavily affected by tidal stresses, and Enceladus must be too. But there must be differences between them, compositionally and also the amount of activity. They're similar but not the same, which is interesting to compare and contrast them. Yeah.
On your flyby where you took a great picture of the North Pole, there were some craters that seemed to be like half craters.
Right.
And it looked like half of the crater had been covered with new material, and I'm just wondering if there was some theory about how that's working.
Right. Thanks for pointing that out, because I forgot to point that out. I pointed out that there are like these swaths of what appear to be uncratered regions that seem to have been emplaced by some tectonic activity. And sure enough, they cut off a couple of craters that were there before. So not only are these regions relatively uncratered, which tell us they're new, but they cut off older material. So some sort of tectonic activity. We don't know what, and we don't know exactly how old, but yeah, definitely something was going on there. Good eye. Any other questions? Oh, one more.
I know that with the Galilean satellites, we were able to look at the magnetic field lines from Jupiter and infer underground oceans or conductors, presumably some kind of salt water.
Right.
Even with the weaker field of Saturn, can we see perhaps changing magnetic fields and infer whether we have the ocean line?
Right. So that it's possible. Now, what it's going to take, though, and we're working on it, but what it's going to take is more flybys. Because of the weaker field, it'll just take more flybys to put it all together. So the magnetometer team hopes to be able to tell us something about an induced field, but they just can't yet with this small data set. So, check back in a couple of years. Yeah.
Will the particles are the particles large enough for us to be able to see them as we saw that plume on Io in any of your flybys?
Right. They are. Now we have to look at high phase. So we're looking when they're backlit. Those images that you saw were particles, like the particles on Io, but they're made out of, on Io, of course, we're looking at sulfurous material, excuse me, and on Enceladus, it's just water grains that we can see. But yeah, it's the same. It's very fine grains, and that's why we can see them, actually. Now, the gas plume is even bigger, and same with on Io. There's gas, SO2 gas, S2 gas, that we can't see. But it's there. You have to just use other methods. Did I answer your question? Okay.
You notice that all the tiger stripes appear to almost in a parallel fashion tilt toward the top. Is that your evidence for a global tipping, or is that just curvilinear? We don't know.
So, yeah. You know what? I don't know. Yeah, people have talked about how, they have a little hook at the end. And I don't know, actually, if that has to do with the reorientation. It is curious, though, when people are looking at that to see what that is. But I don't know if it has to do anything with the reorientation, but that's an interesting idea. Yeah?
I'm sorry to ask another question. I'm just curious, is it spewing out enough material that you could hypothesize that the E-ring is completely composed of material that's been spewed out?
Right. That's a good question. So, people have been looking from the ground and from Hubble Space Telescope, for instance, looking at the gas in the Saturn system and thinking, like they can measure H and O and OH, all these water products, and thinking, where does all this gas come from? Because we know that the E-ring's there, but just basically charged particle sputtering of the E-ring, which is going to produce some gas, is not going to produce the amount of gas that we see. And so the gas that's measured in the plumes now, it turns out, perfectly matches how much gas we need to supply that OH and H and O gas torus that is seen. So things are matching pretty well, that the E-ring is certainly supplied by the amount of material that we see. And then there's loss processes too, like I said, like some of it might be lost as it sort of travels out and then impacts different moons and so forth. But yeah, the numbers seem to work out pretty well for sources of the E-ring.
Can you make any guesses as to when the reorientation took place and how long it takes to happen?
Right. That's a good question. I'm not involved with it enough with that modeling to have to know, but let me think now. The reorientation, the tectonic patterns that we see on the surface that are consistent with it are still there, and the surface is still active. So it really would be a question of, and this is another question that I don't think anybody knows, how long have these geysers been spewing out material? Because, that, if we know that, then we can know, well, how long has there been this low density material underneath? And if we know that, then how long ago did it flip on its side? So I don't know if we're going to be able to answer that just yet.
Characteristics of the E-ring were substantially different than the other rings. Looked very diffuse.
Yeah.
And I'm just wondering is that a electromagnetic kind of phenomenon? Or
well, it's because of the source. The source of the main rings is not geysers from a moon. So it's much more dense. I mean, it was probably like the breakup of a moon or whatever the going theory is now on the source of the main rings. So those particles are going to be larger and more confined. But the E-ring is going to spread out because everything is much more tenuous. There's gas and the particles, and it's just not going to stay as confined because, it's not as dense, and the particles are very small, and they're going to want to travel out and in. they do seem to stop at Titan. Titan is probably sort of constraining that outward boundary.
I'm on a third grader question. If we think that Enceladus is like a balloon and someone has punched it at the South Pole, how long will it take for it to disappear?
Right, yeah, how do I answer that one? How long should this be going? I don't know. I don't know how to answer that. I mean, it's a good sort of thought experiment.
It may take several probably.
Right, and it's also a similar question with, for instance, Io. What's going to happen to Io? Is it just going to peter out and all the volcanoes just stop and then it's dead? Or did Enceladus used to be like Io and it quit and got ice ice on top of it? That's a good question. Yeah.
Why did they settle on aluminum 26 as a potential source?
You know, why did they? I think I can't answer that exactly. I think it's because it was around in that part of the solar system. It's something that we have experience with elsewhere, and it's just it wouldn't be too hard. You know, we can't try for something that would be completely obscure and that we wouldn't believe. So it's doable.
Yeah, I noticed that in some of the larger impacts on Enceladus, it almost looks as though the impactor broke through the crust and some cryovolcanism occurred, like a mushy material.
Right. Yeah. That's what I was like. Those North Polar craters that we were looking at in the last image. It almost looks like maybe the surface was slushy at the time, but maybe slushy is too watery sounding, but warmish, so that the rebound of the material would end up making it look like that, and then it would just sort of get frozen like that. If the ice is as cold as it is today, then it acts like rock, and then you have craters that almost look like craters on the moon, you know, with a central peak and a regular rim, circular rim, and everything. But yeah. When things are mushier and the temperatures are higher, then you get those craters that are deformed looking.
Okay, it's getting kind of late. Let's take one more question if there's one.
Any more questions? You want?
I was wondering if a large impactor would be sufficient to create enough heat to get this southern pole geyser phenomenon.
You know, I haven't heard that considered. That's an interesting idea. I just wonder about a crater. We might need a crater then. You know, who knows? It's good to think of different options. But
okay, I think Amanda will be available to stick around another few minutes if you'd like to come up and ask some more questions. But let's give her a round of applause and say thanks.
Thanks for coming.
And be sure to visit the museum before you leave.